I do that to check the microphone and to wake us all up. Okay. We'll come around to that in a moment so we can actually see the equations. We're going to write down on the board and understand them in terms of shapes and what they actually mean, what a Bayesian's trying to describe to you. So we're in our first example, and apologies if you've already done conjugate analyses in Bayes. We're going to be working through that for the next couple of weeks. So pretty basic stuff. We're going to do it intentionally slow. So kudos to you if it's way too slow. We will be accelerating throughout the class. So binomial example is where we're at. We have to understand all of these terms again, sampling distribution, likelihood functions, and then we're going to get to the holy grail of every Bayesian analysis, the posterior distribution. So let's just remember what we have. We have xi's. They're coming from maybe a Bernoulli distribution. So keep in mind, the sum of Bernoulli's is a binomial. So it's a transformation of Bernoulli's. If I'm talking about Bernoulli's, I can do inference on the sum, or I can do inference based off of the whole joint. They will be equivalent to each other, and we'll see that real quickly. So, but these are going to be Bernoulli with parameter p. So that's the probability of a coin flip. These xi's will be one of either a 0 or 1. So sometimes we think of this as a heads or a tails. I'll put it as a 1 or a 0. So when I say heads, it is the 1, and the 0 is a tails. If we weren't dealing with 1s and 0s, actual indicators, we could re-encode the heads or tails, this qualitative thing, into something quantitative, so that we could encode it as a formula. There's nothing special about 1 or 0 or heads or tails. They're just two different things. And so sometimes when we're just trying to indicate two different things, we use a function called an indicator function. So for instance, an indicator might look like this, that I'll say that when we see the xi's, this is going to be a indicator function. Sometimes people will write this down as a 1, and they'll end up saying that the coin flip, and I'll call that CI for the actual coin flip of the ith coin, just coming up with some notation, is a heads. So I could have called that an H or something like that. This is going to be a 1 if that condition is true. So and I could end up writing down an indicator function with tails in here, or I could say 1 minus my indicator function, where CI is equal to a heads, which would be equivalent to writing down an indicator function, the coin flip is equal to a tails. And so this thing right here is going to be a 1 if that condition is true, or a 0 otherwise. And in our specific case, there's only 2 possibilities, so that's easy to keep track of. We could have this built up with an infinite number of possibilities, and it indicates when one thing is true out of that infinite collection. So very often, I don't use this syntax, the 1. It's kind of nice to think about because it's turning things into 1s and 0s, but very typically, I'll write this down. You'll see this very typically, 1 CI is equal to, let's say, a head. The condition, I usually write it like this. CI is equal to a head. And very typically in statistics and math, they'll talk about a delta function. And that's delta right there. So that's the little delta. So a delta function is an indicator function. There's lots to talk about here. If we were in a measure theory, I might talk about the measure of this thing. It actually is a measurable quantity. If I thought about what it actually looks like, if I were thinking of it as a density function, it's infinitely tall with 0 mass and it has area under it 1. Because everybody knows if you multiply 0 by infinity, it's 1. So it could be, depending on the rates of everything, depending on how fast we're going to 0 versus infinity. So if we're thinking about it just as a discrete object indicating things, we might just write it down like that. So it's just a 1 or a 0. So we're not going to get into those nuanced technicalities unless you guys ask about them, which we might. So at some point. So all pretty basic stuff. So this problem, our sampling distribution looked like this. So this was going to be the product n coin flip. So I would write down I goes from 1 to n, something like that. Or I might write down I goes from 1 to n. Those would be equivalent to me. I could use the MATLAB-esque notation or just put dot, dot, dot. So I'm flipping this coin n times. Very, very typically, people in statistics will do that and write IID over the top of their little tilde. The tilde means it's distributed. What they're telling you is it's independently and identically distributed, meaning that every time we sample from the same distribution, and we do it in exactly the same way. We don't use any previous knowledge from our previous flips. So the P isn't ever changing in that. So this is the same thing as simple random sampling. That's what we call it. So it's the most basic form of sampling. I am not going to write that continually throughout the class. So if I write down what the distribution is with its underlying parameters, and I say those are fixed, and I tell you that's the process, I've told you essentially it's IID. I haven't told you any mechanism for dependence. So my rule in this class is, unless there's a mechanism for dependence, we'll assume that everything is IID. Another synonym for that is conditionally independent of everything. What is the conditioning? It's conditioning on this parameter right here. So we're sampling from these conditional distributions, f of xi given p. Very typically, most people will write that. And they mean given p, p is in their equation, but they don't say conditionally independent. I believe it's such a big deal, and if you think that I'm too pedantic about this, and I could knock it off by saying just independence, that's okay if you believe that. I still believe we have to say it's conditionally independent. Given certain things, those things are independent. So for instance, if I flip the coin over and over and over again, if I knew what P was, all those previous coin flips don't help me to understand what the future is going to be. So for instance, if the P is 0.7, then I think at every coin flip, the probability of observing heads is 0.7. In observing the past, no matter how many times I flipped it, doesn't give me any information so long as P is equal to 0.7 is correct. Now there's a different notion out there, that if I didn't know what P was and I took this away from you, we'll do an experiment soon, just to exemplify this point. If I remove P from you, then you would get knowledge about what P was by flipping the coin. So if I flipped it 1,000 times and I saw roughly 70% of them were ones and roughly 30% were zeros, then I might think P's around 0.7, but I would be learning that through the previous coin flips. So that's why data itself is not independent on its own, because what we actually learn is the distribution and the underlying parameters. If we already know the distribution and the underlying parameters, then the data doesn't help us to learn any of that. But we're in statistics, so what are we actually doing is through the previous set of data is we're learning the model and its underlying parameters, and that's what gives us the ability to forecast. So I'll give you something to think about just real quick. If data itself were independent, which it's not, then observing the past would never help us to predict the future. And we know that's not true. We want to observe the past because we're learning the distribution of the data and its underlying parameters. Please.
So if you're just observing a set of samples, as you said, a set of data, and you're estimating a parameter,
yes,
can you learn anything about whether it's conditionally independent on that parameter?
You probably could, right? So if I were doing everything and it was all ones up front, and then it was zeros at the end, so 70% ones at the beginning followed by 30% zeros, I'd learn there's probably a dependent structure. So you can look at the data and see how it's related to itself to figure out if things are independent or not, conditionally independent, or if there's some sort of maybe temporal structure to it or sequential structure. So the truth is, in statistics, is we get data and nobody gives us the model and says, here's all the underlying assumptions, and you get to know those up front. So usually you have to look at the data and do an exploratory analysis to even figure out what assumptions might be. Then what you usually do is you build up your analysis, you look at your analysis, and you start looking at things like residuals to tell you if you've made any modeling mistakes. So then you go back and you re-engineer everything. So that's a more realistic view of how a statistician operates. There's going to be one fiction in this class that we get to know F, our sampling distribution. We can talk about actual modeling later on in the class, what we actually do. So we're going to take a step back and assume we know what the sampling distribution is, and then when you get into all your research, you'll go, huh, I have to make that. So what you have to do is you have to model your data. And so what I really think in statistics is we're looking at diagnostics, check our modeling assumptions and iterating back and forth. So in reality, it's not streamlined a one-directional process, instead it's a bi-directional process. We'll talk about that later once we get our feet wet and we understand how to do some of the nitty-gritty of these analyses. So yeah, I would say always look at your data first, don't assume anything. So, hard to do. This is IID, so I can product it together. That is, given the xi's, or xi's given p, I can make this statement. I can write everything down as a product because everything is conditionally independent. So I have to have the p built into that equation to even make this independent producting happen in the first place. So what does this look like? This was just p to the xi, 1 minus p to the 1 minus xi. Because the xi's were just these indicator functions, ones and zeros. And so this is just turning on p or 1 minus p, depending on if that's a 1. If this is a 1, this whole equation right here is p. And if it's a 0, it's 1 minus p. So it's just a statement about 1s have probability p and 0s have probability 1 minus p. When I product all this thing together, I wind up with p to the sum of the xi. I goes from 1 to n, and 1 minus p, n minus sum of the xi's. So if I just sum together the exponents, that's what I wind up with. And we notice something interesting. Everything, all the information about this joint distribution, what I'm kind of thinking about right here is this was a joint Bernoulli. This is the probability statement, but I don't actually need to know the full sequence of 1s and 0s. All I need to know is the sum. And so instead of that, we could talk about the distribution of the sum. And so for a binomial distribution, we wrote down that the binomial sampling distribution ends up looking like this. I'm just going to re-encode some new variable. So instead of talking about the sum of the 1s and 0s, xi's, I'm going to give it a new name. So this is very typical. So this is going to be z, I'll just call it that. So this is going to be the total number of successes, where I'm going to define a success is a 1, and a failure is a 0, just following our typical convention. Poor zeros, tails on a coin. Why did they get failure? So anyway, so that's what we got. This thing right here is binomially distributed. It's a one-dimensional creature where the 1s and 0s, the vector, is an n-dimensional creature. And I can do inference based off of this and get exactly the same inferences. So the sampling distribution, fz given p, but still the underlying parameter is n choose z, p to the z, 1 minus p to the n minus z. And in any stat class previous, they would have taught you what a Bernoulli or binomial distribution is. This is the binomial coefficient, so which just counts the number of rearrangements of ones and zeros in a vector of n coin flips with a fixed number of successes, with z successes. So this is the total number of ways that I can reorganize a vector of n bits, zeros and ones, with a fixed number of z successes and restring them all over. So it's just a combinatorial argument that hopefully you're all familiar with. So that's the binomial sampling distribution, and this is where we left off last time. Then we said one more thing. We said the likelihood function looks like this. Get rid of this. Binomial, and I'll say or joint Bernoulli, doesn't actually matter the way you think about this. So keep in mind the joint Bernoulli look like this. Sum of the xi's, 1 minus p to the n minus sum of the xi's. I'll be a little bit lazy and not put my indices down, since we've seen them already. So that was the joint distribution for the vector of zeros and ones. So 1, 1, 0, 1, dot, dot, dot. There's n of those things. That's what that represents. It has this distribution. And the binomial distribution is very similar. Remember, these are just the sums of the xi's. So this part looks exactly the same. But the normalizing constant is different, because the number of ways we can count things has been changed. We've moved from an n-dimensional space to a one-dimensional space. So the binomial sampling or the binomial or joint Bernoulli likelihood looks like this. I'll give us some notation. Given z, it's going to be, I'm going to write down equal, but I'm going to change this later on. So I'm going to just put this in quotes, because we don't actually mean equal right here. If you do use equal throughout the class, and you say, I always use equal, and I take it to be equal to whatever, you will never make a mistake so long as you always use your likelihoods appropriately. That is, they always come in the form of a ratio. So all your arbitrary normalizing constants will cancel each other. So the likelihood function looks like this. N choose z, p to the z, 1 minus p to the n minus z. And when I write that down, it looks eerily similar to the sampling distribution. It looks exactly the same on the chalkboard. But if we follow my convention that everything to the right of the bar, which not everybody follows that convention, but in this class we're going to stick to it. If somebody wants to change it later on, you'll at least know how to translate. P is fixed in this equation. So I need to know what P is to come up with the total number of successes. What that means is I need to have coin in hand to be able to flip it to generate the ones and zeros. What do I need to do that? I need a coin with a fixed probability. Otherwise, I can't generate the ones and zeros in the first place. There's no coin to flip. So P is fixed right here. There's a coin that I'm flipping, and this is what's random. So that's the random component. Where in this thing right here, if we follow my convention that everything to the right is fixed, this is my data that I've observed. So this is fixed, i.e. it's observed data. And this right here, I'm not going to say it's random, because random is reserved to mean something special. So a random variable in statistics has special properties that if I sum over a random variable, whatever its density or measure is, it'll sum to 1. So it follows Kolmogorov's axioms. It has all of those properties of probability that we're familiar with. This is just a variable. So I'm just going to say it's variable. It's not yet a random variable. It doesn't have all of those properties. So if I add over p, it may not add to 1. So if I integrate this, I'll remind us that p lives in this interval, 0 and 1. So that's a continuum. So where this thing right here, this z, lives between 0 and n. There could be 0 successes, or all of them could be successes. So for a very, very big p, you might see a vector of 1s. So these are entirely different functions right here. So that's the likelihood function. I'll point out that this right here for the Bernoulli has exactly the same shape. So if we think of this as a function of p, the function of p appears here. The z's are really just some of the xi's. And so this has the same shape. So this function as a function of p is exactly the same. And in terms of writing it up to proportionality, the only thing that's different is a positive constant sitting out in front. This has a positive constant sitting out in front, it's 1. We usually don't write that down. So they only differ by a constant, but in terms of a function of p, they really do describe the same curves. They're just shifted up and down. So if I multiply it by some positive constant, I'm just taking that curve uniformly and lifting it up and down. I could add a number to that and do the exact same thing, but that's what a positive constant will also do. So it just lifts this curve up and down. Likelihoods are self-relative, meaning they can only be compared to themselves. So meaning that the curve itself, let's call this a function of p, say that this is the likelihood function of p given z, it might look something like this. Try to come up with something realistic. So might actually look like that. It doesn't have to be symmetric. So if I reflect around its mode, it doesn't have to look this way, but this is a typical way that this might look if n is big. We'll look at this in a second. This lives between 0 and 1. So if I'm going to talk about the likelihood of P1, some point right here, that's its likelihood value. So, and I'll call this L1. Or I look at some other point, let's call this P2, right here, in its likelihood value, let's call that L2, that these points should only be compared to each other with its relative height in mind. So how do we do that? We take ratios to do that. So if we take a difference of these things, a positive constant might make a difference in what we're actually comparing to each other. And so if we're going to compare the likelihood of P1 to P2, we're going to look at this ratio. So I'm going to look at L1 to L2. So P1 to P2, the likelihood is going to be, the way to compare it would be through this ratio right here. And because this is a little bit smaller than that, this would be less than 1, but if I compared P2 to P1 in the opposite way, that would be greater than 1. And so a likelihood ratio, the only restriction is that it's positive because we're going to be taking values from a positive curve. So keep in mind, densities or mass values are always positive. That's what we use to come up with this likelihood function, so those are always positive as well. They can live between 0 and infinity. I'll just point out that no matter how I form this, if I use the n over z in here, and that was in this likelihood measure, it'd be in both the numerator and the denominator, and they'd cancel each other. If I ended up using this likelihood, and I changed this to x and not z, I would have a 1 that cancels each other right there. So any positive constant that I multiply will cancel each other. So the likelihood function and the likelihood ratios that we would get from the Bernoulli or the binomial are identical to each other. So the way we would use them. So that's something to be aware of. So likelihoods are self-relative and they're proportional. They're the same up to any positive constant. So let me write that down. So likelihood functions. Likelihood functions have the same algebraic relationship between the data I'm going to call this X, although I've used the data to mean different things. Z is data, it's a transformation of cap X. So I could have used some of the XI's, that's just data as well. But X itself is all of the data. Before I was calling this D, and I'm going to start switching over to cap X. So the data and the parameters. Usually I'm going to call those theta. In our example, P is our parameter. So that's theta. So I'm going to start talking about this stuff a little bit general, but I'll give you examples along the way. So there's only one parameter in our analysis. So likelihood functions have the same algebraic relationship between the data and the params as the sampling distribution. Or density, depending on if we're in a continuum or a discrete space. So they look like the same formula, but are functions of theta, the parameter space. So that's what we've done here, is we took the sampling distribution and I just thought about it differently. I plugged in Z and I thought about it as a function of the parameter space. And that's how I got here. So that's the likelihood. So really, likelihoods, theta, given X, are going to look like f of X, given theta, but are functions of this. This is fixed, which probably means this f is inappropriate to call it f. Very typically, you'll see people use Bayes' theorem just like that. They'll say our sampling distribution is f, and so our likelihood function is also f. And they'll slot that thing right in, and they think they're doing you a favor by not confusing you by recycling the same terms but using it two different ways. And maybe for some people that's totally fine. So they can live with that abstraction. I'm going to be really clear about it and make this a function of this, but you take your sampling distribution, you write it down, you take all of your positive constants, you throw them away. That's what this means. So this is proportionality. And what proportional to means is I can multiply it by any constant. So I can just multiply that constant in there and forget to even tell you about it and just get rid of it. My favorite constant to multiply is 1. In all of the calculations we do with this constant right here, we're just going to see it cancel from the equations anyway. So that's what a likelihood is. Let me show you a picture relating to our example. Eventually we'll get to a point So this is a particular binomial sampling distribution. Keep in mind, the binomial distribution is a whole collection of distributions, but as soon as I tell you what P is and what N is, I've told you a specific one. So to draw this histogram, I needed to tell you P and I needed to tell you N. So N was 10 in this, and P is 0.7. So that's what it is. So these are the probabilities of observing all of these different values that sum up the ones and zeros in a sequence of 10 coin flips. So what's the probability of seeing 0 successes in 10 coin flips with a coin probability of 0.7? It's tiny. So you can't even see that. It's vacuously small, but it's not 0. It could happen. So probability of only observing 1, if the probability is true 0.7, that's really small. What's the most likely thing to happen? That's the 7. So 0.7 times 10 is the expected value. And I'll let you check that out. So n times p for a binomial is the expected number of successes you expect to see. And we could teach that probably in elementary school. So how many times would we expect to see this? If we expect to see 0.7 successes on average for each coin flip? I'm not sure we can talk about it that way. So that's an abstract idea. So times 10 though is 7. And so that's the sampling distribution. It's a histogram of sorts. It's not a data histogram, it's a very special type of histogram. It's a distribution. So all of these bars have the same width, and if I sum up the probabilities for each one of those bars that are denoted over on the left, it'll sum to 1. So meaning that we've summed over every possible event possibility in the space. The likelihood looks different. The likelihood is a curve that lives between 0 and 1. It's a function of p. So what did I need to draw this? I needed whatever our number of successes are. I apologize for my notation. I called that x is equal to 3. Following our notation on the board, that's z. So there's 3 successes out of 10 flips. Where did I come up with that? I didn't flip the coin. I just drew you a likelihood function and plugged it in. So that's the same as taking this thing right here, plug it into 3, that at 10, that at 3. It will produce that curve right there. This would be possible. What's the probability I'd only see 3 successes out of 10 coin flips? Small, but possible. Let's say I got that. That would be the underlying likelihood. And so where would it peak? It would peak at 0.3. So 3 over 10. So the fraction of the number of successes. And it would tell us relatively how likely certain values were. So it would give us a method for doing a comparison for comparing different values of what we thought P was. So we might think if we saw this likelihood curve, P's 0.3. But the diffusion of the curve, the flatness of it is telling us there's other reasonable values out there that it could have been. And keep in mind the original process was random. So how does Bayesian account for randomness in the process, the frequency of everything? They take the sampling distribution, same thing everybody else uses, and they envision it differently. It's a likelihood. So, and that's what these look like. Any questions about that? Okay, so let me just ask real quickly, what is that sampling distribution called? Binomial. What is that curve called? That's the likelihood, but we use that term universally throughout all of statistics. Any sampling distribution or density I could turn into a likelihood just by envisioning it differently. This one's specific. That's a particular shape, and the shape is described by this function right here. Anybody know what that function is called? What might we call it? We're going to need a name for it. Anybody ever see anything like that? Looks like a beta. So what's that? Is it a beta function? It's not. A beta function is actually the integration of that. So it's what I would call a beta kernel. Let me show you a new distribution. So I'm going to call this the kernel of a beta. Kernel. Let me show you a new distribution. Some of you will have seen this. If you've had probability lately, you've probably seen this. This is our second distribution that we're going to become familiar with. We're going to use this a lot in this class. So if you've never seen this before, congratulations. So this is called a beta density. Very often I'll just describe them as distributions, but the distribution would be the integral over the density. So it relates to the probability statement, technically. So the beta density looks like this. P to the alpha minus 1, 1 minus P to the beta minus 1. This is an actual probability distribution. I'm going to write it down like this, and this is not normalized. So it's proportional to that. Does anybody know what the limits on alpha and beta are? For this to actually integrate to something that we could normalize and integrate to a positive quantity, we need limits on what alpha and beta are. Anybody know? Greater than 0. So in fact, so we're going to just say these are going to be greater than 0 right in here. Oftentimes people will use zeros in here. It does make things improper, so be careful. On the way Bayesians will sometimes use these distributions. Sometimes they'll include the endpoints. We're going to see examples of that. So this is typically not allowed, but people often will use that as an analysis. This is called Haldane's prior if you include the zeros. We'll talk about that later. So if I want this to integrate to something between 0 and 1, I need to normalize this. So our normalizing constant would look like this. So if I came up with some constant, this is our normalizer. This is going to be the integral of P to the alpha minus 1, 1 minus P to the beta minus 1, dP. And this is a definite integral, so I'm going to integrate between all the valid ranges of P. It lives between 0 and 1. It's a probability. Somebody picked 1 as special and 0 as special a long time ago, so we're going to stick with those. So what I'm going to do is I'm going to divide by this number. So I would end up taking C inverse and plug it in right there to divide by everything. It's the same as dividing by the sum of everything. So that's just going to normalize it. It's all positive, and so it will add up to 1 now when we do that. So this is a beta density, and integrating over it gives you a beta distribution. And it models probabilities. So does anybody know what this function right here is called? This has a special name. This is actually called a beta function right here. So if you go to MATLAB or Mathematica or something similar and you ask for beta function, it'll actually talk about the integral of this thing. So, and it can also be represented with relationships to the gamma function. And if alpha and beta were integers, it would have a relationship to factorials. And we'll see that later on. We'll see some simplifications. The good news is you really don't need to know this thing because it's just all normalizing constant. And the way I'm giving that away is by writing this proportionality sign. So every time I write down the proportionality sign, you might think to yourself, whatever that junk is out in front, probably don't need to know. And I'll give you an even bigger heads up. When you need to know the normalizing constant, I will tell you that it'll be something useful for the class. This one you'll never actually have to compute. I'll never ask you about a value for it per se. But if you were doing a beta predictive analysis, you might need to know about that function. So we won't do it in this class. Okay, so still moving really slowly. That's a beta density right there. So the kernel of the likelihood, the important stuff, the thing that gives it shape, looks like a beta. So We know this. We know what that is now. Now we need to work on our posterior distribution. Let me rewrite Bayes' theorem a way that I haven't written it down yet. I think it does appear in my slideshow, but this is another way of writing down Bayes' theorem. This is our week 2 way of writing it. Bayes' theorem. I'm going to say our posterior distribution on theta, given our data. So I'll just be using these as general parameters to generally notate something. But this is going to be proportional to the likelihood function for theta times pi theta. This is the likelihood. And this is the prior. So it's what we might believe or model our ignorance through before we observe the data. So the language is, before we see the data, here's our shape description of what we believe maybe theta is. Could be flat, could model ignorance. I think it's the same everywhere. Could be something different. Very typically, making it flat is not a good idea. And even in this analysis, it's not a good idea, although it's wildly tempting. So from an intuitive standpoint, we can use that and see what it does. Probably nothing dramatically wrong. It's just that I can always beat you in some sense by doing something else. That's what this class is going to be about. And likelihood function. And this is the posterior. So this is what we think about theta after we observe the data. So we have our prior beliefs, and we update through our likelihood that contains the data to come up with our beliefs after we observe the data. So that's the superposition, i.e. the product between these two things. Your prior beliefs superimposed on your data-driven beliefs. That's what a Bayesian does. What I want to point out is if theta was multidimensional, there would be a joint characterization between the parameters in likelihood, and you could think of the prior as a penalty function, some sort of a weighting penalty. And we've all penalized things and done things with penalties before that says stay away from this part of the space. There's nothing good there for you. And we'll see examples like that, especially pertaining to this. So if you don't like the terminology, what I think before I see the data, because I didn't think anything. So, and what I thought after I saw the data, you could just think of this as likelihood times a weighting function. And all Bayesians do that. That's the Bayes operating procedure. Is it Bayes' theorem? Kind of. So it kind of looks like this. F of x given theta times the margin on theta, and then I did not normalize by the right normalizing constant, our margin on x, and that's Bayes' theorem. So if you think of this as the sampling distribution, then it looks like Bayes' theorem. Why don't I like to write it that way? Because this is a function of theta. And it ruins everything I think about what that bar means. So it's just a heads up to everybody, it's a function of theta. So it looks like Bayes' theorem. So all Bayesians, or at least parametric Bayesians, are taking the likelihood and multiplying it by a prior. Let me give you a definition. This is a particular class of prior, and we're going to keep reconfronting it. And the reasons I tell you this is a good prior in this lecture and next time aren't very good reasons. And those good reasons are going to keep coming throughout this class. So I'm going to start you out with weak reasons to like this class of prior. And then I'm going to tell you later on, it turns out a lot of very optimal choices are members of this class of prior. Okay, so we're going to start out with something intuitive, and then we'll get more mathematical rationale for liking this prior later. It's called a conjugate prior. Be careful if you've ever seen this word conjugate before. If you've seen it in other fields, it means something entirely different. It doesn't mean any, so if you've been playing around in linear algebra or complex analysis, they all mean different things. We also have our own usage of the word, and I don't see any overlap. So in the way people use this word. this is what a conjugate prior is. I'm going to call my prior pi theta conjugate. Usually I won't write that down. We'll just recognize it as a conjugate prior. So this is going to be my conjugate prior. It's going to have a particular property. So if pi theta will remind us that it is a conjugate prior. So this if is going to be it is. So pi theta is a member of some family. This is going to be a family of distributions. I don't mean anything as wide as the exponential family, which is a family of families. So that's your extended family. I mean actual, like, close-knit family. So people that you have to claim as your family members. So in statistics, lots of distributions belong to the exponential family. So tell me two distributions that belong to the exponential family. Normal, you got one.
Exponential.
Exponential, yeah, that's good. So exponential and normal. We're going to say those are both their own families. So an exponential distribution is defined by one parameter, lambda, and that parameter, by changing it, changes the family member. So all exponentials are members of their own family. All normals are members of their own family. We don't have this big, broad family thing. So normals are normals. They're members of a family. How do I change the normal membership to the family? I change its parameters, mu and sigma. So for a beta distribution, they all look like that. Alpha and beta are variables and they're placeholders, so that's an infinite collection of beta distributions. As soon as I lock down alpha and beta, I have one member of that beta family. So that's what I mean here. So a family of distributions, e.g. normal, exponential, beta. So this would be one of those, not all of them. One of them. And if pi theta given x, our posterior distribution, is also a member of that family, not the exact same family member, but if this was a normal, this would also be a normal. If this was an exponential, this would also be an exponential. And all we've changed is the parameters underlying that distribution. Then we'll say that the prior is conjugate. So if these both live in the same families, these are the same, then we say that the prior is conjugate. So what we're going to do to look at that is we're going to look at pi theta given x. Remember, the only things that involve theta, which is what the distribution over, are the likelihoods, the likelihood function, and the prior. Those are both functions of theta. Whatever I divide this by, integral likelihood theta given x, pi theta d theta, definite integral. This doesn't involve theta. So there's no shape with theta in the denominator, so I can get rid of that and just talk about what I need to understand in terms of the shape, the beliefs concerning theta in terms of the wiggles of this shape. They're all involved up here. So what I need to look at is if I multiply that by the likelihood, does it have the same functional form as the prior? And if I didn't change the functional form, the prior is known to be the conjugate prior. So just very, very quickly, let's look at the likelihood function. You can never figure this out without staring at the likelihood and playing a mental game. What do I need to multiply here to retain its form? So how do you really do this? You know all your distributions. And you kind of cycle through them. Nope, that one doesn't work, that one doesn't work. And eventually you get good at it. So let's just look at this for our analysis. Our prior, this is all going to contain p. This will be a p right here. Our likelihood is going to be p to the sum of the xi's. 1 minus p, n minus some of the xi's. I goes from 1 to n, I goes from 1 to n. Eventually I'll stop writing in all my indices, save a little bit of chalk. But the question is what does this need to be when I multiply it through by this to still have the same functional form after the prior slides across the likelihood? You'll hear people use that language. Slide the prior through the likelihood. What do they mean? Multiply.
Does it need to be a beta?
It needs to be a beta. We'll come back and we'll pick up with this next time. If I multiply p to the alpha minus 1, 1 minus p to the beta minus 1, then over here I wind up with p sum of the xi's plus alpha minus 1, 1 minus p to the n minus sum of the xi's plus beta minus 1. The beta coming from the prior, the alpha coming from the prior, they're getting added in. What is this thing? This is some other beta density, and these are its two arguments. So conjugate analysis is just updating the arguments. A priori, my beliefs were expressed through those two arguments. We have to, of course, come up with what are reasonable alpha and betas, and how do they change the distribution, and what's the influence. There is an answer to an optimal choice in some sense. I'll have to tell you what optimality means and what the sense is about. It's actually something good, and I use it all the time. Must be good. So this is some other data distribution, and it's been updated with the data. And that's where we get the terms from. So we'll come back and do that a little slower next time, talk about this beta distribution, think about what it's encoding, how it's weighting the analysis. But we can kind of see in this that the betas are weighting the analysis. The alpha and the beta here are weighting the analysis just like data. It's acting very similarly to data. So it has a weight that is comparable to how the data influences the analysis. So we can think about it like that. The question is how much do we want our data, our prior to be worth? So if we wanted it to be worth 2 data points and it's equal, I might say alpha is 1 and beta is 1. I'm encoding the prior like 1 success and 1 failure. Why would I do that? Let's come back next time on Wednesday, pick up there, do a simulation study. Once we're comfortable with that, we'll move to other analyses. I've taken up 7 minutes of your time, 6 minutes of your time, and 4 minutes. So I owe you 17 back right now. I'm keeping track. Thanks, you guys. Have a great afternoon, and I'll see you on Wednesday.
I'm just going to keep track of it. I think it's 15 minutes. Just skip class.
I'm a great approximator.
I was going to say, you're going to wait. Well, eventually we'll get up to 50. And then
I'm a self-graded. Yeah, exactly. I'm going to give you a day off in the future.
prior week.